Welcome to this video where we explain a few more practical applications for to Lenz's law, to induced voltage and induced current. Now, one of those applications is called eddy currents. They're sort of currents that go around inside of a conductor when it moves through a magnetic field in and out of it. When it does so, it will actually encounter a sort of braking effect. Why? Because let's, for example, take this picture here. If you swing this copper plate, this conductor, through a magnetic field, it is going to try to generate a magnetic field of its own, trying to create this sort of, well, let's call this counterclockwise rotation of current in here. That creates a repelling magnetic field because you go from zero flux to an increase of flux, and that will always try to repel, right? As it moves out of it, that current is going to turn around because it's going to want to create a magnetic field to undo the change and keep it there. In practical terms, it means that it's constantly going to be trying to fight and break that movement. How can this be practically used then? Well, technically there's a few applications like this. If you, for instance, take this joyride, you can create a braking effect without the need for any mechanical components to do the initial braking. Traditional brake pads, first of all, they're not 100% reliable. They can break because they have to use friction and they're going to wear down. You can do your initial part of braking very easily using these eddy currents in conducting material if you drop this inside of a magnet. A similar use of eddy currents, for instance, is in this case when you have a training bike. You can create these eddy currents inside of the flywheel, depending on the size of the magnetic field created in here. So you can actually adjust the braking power of your flywheel, so you have to fight harder, you have to pedal harder to fight against it. So you can actually get a bit of constant braking without the need for brake pads that are going to wear out over time. Another practical application of these eddy currents is actually used in an induction cooker. Now, if you consider an induction cooker, there are three main components being used. The first of all, you can't just use any pot for this sort of cooker. It has to be one that is adjusted to an induction cooker. Technically, this is ferromagnetic, and in practice it will also have these sort of lamel structures in it, but don't want to talk too much about that one. It doesn't really matter. The most important thing is down here. Underneath your cooker itself, you will have electromagnets, and these electromagnets will have a high frequency of change in them. I'm just going to move this to a more elegant spot. There you go. So they're constantly swapping sense inside of that electromagnet, so you will get a high frequency change in magnetic field, which will introduce eddy currents into the pot you put on top of it, and that actually creates the heat in this case. This doesn't work like any traditional cooker. On top of it, you of course have, because you don't want to place your pot directly onto the electromagnets, you have either a glass or a ceramic plate, right? But it doesn't work like any traditional cookers because it's not like the ceramic plate is being heated up. You're actually directly introducing heat into your cooking pot through these eddy currents, which, well, we've discussed the Joule effect, which creates heat inside of the pot. That heat is then going to be transferred to the thing you're trying to heat up, but also, of course, a small amount of it is going to go back into your ceramic plate. So there's no energy being directly poured into this ceramic plate to try and heat it up and therefore transfer your heat to your pot and then to your food. You're directly heating up your pot through this system, which means these cookers are incredibly fast. Your pots and pans will be at an insanely high temperature in a matter of seconds through this system, compared to the much slower traditional cooker, which has to transfer its heat to the pot first and then from the pot to the actual food itself. Now, other practical applications. If you cause eddy currents inside of these metals, they are going to be heating up. And this is also how a metal detector works. A metal detector actually detects a change in temperature underneath it. If this doesn't encounter, like this thing is constantly sending out changing magnetic fields, right? Unless it encounters anything metallic, you're not going to get eddy currents. As soon as there is a metal item underneath it, it's going to have eddy currents running through it. That thing's going to heat up, and that heat can be detected through an internal sensor, and then you know, like, there is a type of metal underneath it, might be worth digging it up. So a metal detector is based on that technology as well. A and D are actually incredibly similar. When you walk through one of these things, remember, if you've ever taken an airplane, it will ask you to take a few belts, take up any coins, take anything that has metal clasps off, because you will be stepping into a changing magnetic field line, which has no effect on your body whatsoever. It's perfectly healthy. However, if there are any metal items on you, of course, they're looking for guns and knives and all sorts of things. They will heat up, and they can easily be picked up by a temperature sensor in this case. So both A and D work via eddy currents, which is something I will write down at the bottom here. Are metal detectors. When exposed to a high frequency change in flux, you will create eddy currents. It heats up, and then it can be detected via a temperature sensor. So that's essentially how metal detectors work in this case. That also concludes our chapter about induction and electromagnetism in general. The next one will be about nuclear energy, and I hope to see you there as well. Bye.